Hi everyone. Our topic is toward a low-cost disdrometer, measuring drop size with a cantilever piezo film. I'm Wei Qilin. There are many types of disdrometer now on the market using different techniques, like optical, impact, acoustic, and radar. They all have different advantage, but they are more high-end products, which means they cost a lot for good qualities. So we want to develop a disdrometer that is low cost and still with a decent accuracy. The way we choose is piezo film in the top left image. The reason we choose piezo film is the potential of energy harvesting. If the device can run with the chargeable batteries, some energy harvesting techniques can definitely help it. The film has several characteristics, which is low cost, consistent, small, easy deployed, and the potential of energy harvesting. So we use needle to control the drops. Needles have 7 different diameters, so they can produce 7 different sizes of droplet, from 2 millimeters to 3 millimeters. And the piezo film is clamped under the needle. We treat our piezo film as a damped cantilever beam. In this assumption, we can successfully simulate signal of single drop. The equation is at the bottom left of this page. It is worth mentioning that the algorithm we choose to determine how good a simulation is using dynamic time warping, because there could be a lot of reasons for the signal to stretch or offset, including residual liquid on the film, normalized thickness of the film, and error in the measurement of the film length. So there are not only phase shifting, but also periodic difference. So if we use Euclidean distance directly, the result would be extremely unstable because the algorithm would adjust the signal amplitude to fit the real signal. But amplitude is the most important variable to determine the size of the droplet, so we use dynamic time warping to correctly map the simulation signal to real signal. Knowing that we can approach to signal with equation, we then do it on all different sizes of drops. There are some key variables that influence the simulation result the most, which is droplet weight, damping ratio, droplet force, and normalized substrate thickness. We first determine thickness, because thickness will neutralize the influence of droplet weight if we free this variable. So we free thickness first and then fix it with the mean value we get. You can see how droplet weight and substrate thickness normalized with each other in the left graph. Different sizes of droplets all mixed together. We can separate droplet easier with limited substrate thickness, like it shown on the right, so we end up fix it. However, even we fix the substrate thickness, the result of simulated weight does not have good relationship with the real weight. Like we see on the left, the R-squared of their linear relationships is only 0.38. A simulated droplet force have a good relationship with the real droplet weight. The result shows that they have a linear relationship and the R-squared is 0.94, which is really good. So we can conclude that we can map the simulated force to droplet weight. We have confirmed that piezo film have the ability to measure droplet size with quite good accuracy. However, the range of the size of the droplet is not small enough, and because the film needs 5 milliseconds to back to its original state, how the film vibrates with overlapped droplet is unknown yet. Also, film have different reaction when droplets hit different spots. And most importantly, expose piezo film directly to rain might not be a brilliant idea, so we still need to make different protocol to protect the film from various damage or even improve its accuracy. Due to all these reasons above, we have made an equipment that will make our work easier. We use stepper motor to control the position and micro pump to control the flow rate of the droplet. More results will be available soon. Thank you everyone for listening. This is my report.